He's telling us that every time you have a cycle, every time you have a the sine wave, every time you have a circle, every one of them, in every one of these cases, each one of these cases, that sine wave, this right here, this one single sine wave, right? There's two sine waves here, though. There's three here. Okay, each one of them get an H worth, a Planck's worth of joules. This one, all these sine waves get the same exact amount because it's quantized into, just like eggs. You got so many eggs. An egg is worth something. Okay, so much money. Well, each one of these waves, right, just a whole sine wave, gets this H amount of energy. Okay, this gets 1 H of that energy. This gets 2 H's of that energy. This gets 3 times as much, 3 H's. And why? Because each one of these waves, a complete sine wave, is worth 1 H, or 6.626 times 10 to the negative 31st. Every one of these waves get that same exact amount, because you know why? Because H tells us you get that many joules per cycle, per sine wave, per circle, per cycle, per wave. But he's also saying this. He's saying every second, right? Every sine wave, right, is like a packet of energy, a photon, right? And it alone stands alone, right? And every second is a photon. Okay? So this is a second, this is a second, this is a second. They're all photons, right? This photon has how much energy? How many waves does it have? It has 1 wave. So that's how much energy it has. It has H worth of joules. That's H worth of energy. Okay? How about this guy over here? He has 2H. Why? Why does he get 2H and this guy gets 1H? Because every wave, or every circle, every wave, it gets H amount of energy. This guy has 2 of them, right? And if each packet, if your packet is only 1 second, right, then that's what this packet has. This packet has 2 waves, 2 cycles, 2H. This one here, this packet, right, this 1 second packet, right, this packet here, it has 3H. It has 3 cycles. It has 3 circles, 3 waves, 3 periodic sine waves. So he gets 3H, because each one of these waves, no matter what wave you're talking about, each one of them, sine wave, each one of them gets H amount of energy. So what is Planck's constant? It's the energy you get per cycle, every second. In a packet of because your photon's only going to be a second, say, okay? So there you go. There's a photon, there's a photon, there's a photon. H, Planck's constant says that, each one of these waves in these packets gets 6.626 times 10 to the negative 34th joules. That's what it's worth. That's the energy that is equal to this, right? And I want you to keep in mind, when I'm saying this is it is 1 second, this is 1 second, and this is 1 second. That's true, okay? But this is just arbitrary. A photon, I want you to think of a photon as being 1 second, long, a packet. Because that's what the equation says, okay? It's one second. The reason why we have it as a second, and he put it as a second, because that's what we have, that's our time units are based on a second. What else are we going to put it at? Could have made it 2 seconds. Could have made it 4 seconds, you know what I mean? He chose a second, because that's what was normal. So nobody knows how big the photon packet is, you know what I mean? Is it 1 second? Is it 2 seconds? No one knows. Is it just 1 sine wave? Most likely it's just 1 sine wave. Or, it's just some arbitrary, unit of time. But we use it, so you can think of it this way, though. You know what I mean? It's easier to do, it's lines up with the math. Most physicists today, they don't even believe in photons, even though what's funny is the more evidence they have to prove something, the more they say it doesn't exist. It's funny. On this whiteboard, right, is that this right here, okay, you can see this is B sub F, function of T, temperature. Okay, it's this formula right here, right? It's exactly this formula. You might say, well, this has a C2 square 2, and this has permittivity and the permeability, right? What's the deal? See, this is what I'm going to go over this more in another videos or whatever, but this is what confuses people. You know what I mean? They need to start writing out their formulas correctly. You know what I mean? This way, okay? And then tell you, hey, you can put a C2 there, right? C squared, and it'll be a lot easier math. You know what I mean? You don't have to, look these up. You know the speed is light, and you have a square button on your calculator. You know what I mean? You don't have to deal with tens to the power of this. But this is the way it should be taught, because this is the correct way. Okay? This is gibberish. Okay? This is gibberish. Okay? It's right. Don't get me wrong. But it doesn't tell you what does C squared stand for. What does it stand for? I don't know. This is what it stands for. So why not write it down there like that? This is what, not every time, but most times when you see a C squared, this is what it means. It means E naught 0 and mu naught 0, or whatever you call these things, with permittivity and permeability. That makes sense, okay? That makes sense. Like up here. See up here? What's he got? He has C squared right here. Now look what I got. I got the same exact formula, but I put the E naught and the mu naught there, right? This is proper. This is correct. This is still correct. I'm not saying this isn't correct. This is the way it should be done, but when you're teaching it, you should not, no teacher should be having no C squared in their freaking equations, man, because nobody knows what it stands for. Okay, it always stands for this though, or some type of, depending on, you can tell what it's talking about. Is it talking about impedance? Is it talking about permittivity? Is it talking about permeability? Is it you know what I mean? There are constants that we know they're talking about what they're talking about, because we can relate it to it. You know what I mean? If you're talking about magnets or whatever, then it's C, or C squared usually represents some form of this. If you're talking about electricity totally and that's it, it's usually talking about this. You know what I mean? But people don't even know anymore, because they don't tell you. They don't tell you. But anyways, now on the, when I was just saying about how changing the constants, C squared, put in, these, now that, I don't know. I just started calculus. Those are function equations, okay? They're not like this. If they're like this, then yeah, change. I'm not 100% sure that you could change them in those instances. I was just bringing it up as an example. But to tell you, to show you what I'm talking about, here's the force thing for equation for two charges, right? The force that they have, and here's the equation for if you have Earth and you're falling or something, what's the force? Two masses, right? And look, they're the same exact thing. They got a conversion factor. They got two things they're multiplying, two things they're multiplying. R squared, R squared. It's the same formula, man. But why nobody seems to know, like this KE, right? This that actually represents 1 over 4 pi E naught. Okay. See, if they hide it inside that K, how are we supposed to know? A lot of people don't understand this. R squares always means, that this something happens and it goes out as a sphere, right? And that sphere has the same exact power or energy, whether it's small or big. So the bigger it is, that means it has to distribute that same energy. If it has the same energy, right? It has to distribute it along a lot more bigger area or whatever, you know what I mean? So that's why 4 pi r squared, that's the surface of a sphere. And that sphere is the force going out, you know what I mean? and it gets weaker and weaker the further away you're away from it. You know what I mean? But I want you to think about it now. Look at the, see, now we know, because they tell us the K has this in it, you know what I mean? But look at this big G. That big G, that is not G. This right here is not G, because we know that the formula has to have 4 pi in it, okay? I don't know about to see, I don't think that E naught should be in here, because this isn't really about electricity. But we know damn well this is an inverse square law, which means they are taking, this G is G plus they incorporated this 4 pi into it. So we don't see it, and now we don't relate it to, hey, this R squared is so that we can have the sphere. You know, just like down here, we're taking the area of a sphere. So this G is a lie. Now I wanted to bring up one more thing about these, 2 pi rad per cycle, and what a rad is. Like I said, when you take a sine wave and you flip it on each other so it makes a circle, it's not really a circle, it's an oval, right? Now I'm saying 2 pi rad per cycle means 2 pi radiuses per circumference, right? 2 pi r equals circumference. So a rad is just a radius, okay? And if you see right here, your radius is going to be, you can't do a radius with like an oval like that. So you have a big radius here and a small radius here, right? See, the radius, it's not really a radius, okay? What they did was they took this sine wave, right? They made it into a circle, right? They flipped it over, and they chopped it up, just like I chopped this real circle up, right? They chopped it up into 6.28 parts that are all equal, just like you would do if you had a circle, you know what I mean? A rad is not a radius, right? Even though you should think of it as one, but it is 1/6.28 of the whole circumference, right? So 6.28, that's 2 pi. 2 pi radius equals circumference. 6.2, that means they cut this up into 6.2, you know what I mean? Arbitrarily. The size depends on the circumference. If the circumference is bigger, then your radius is bigger. But it's related to that because you do your stuff with, in cycles. So what's a whole cycle? It's 6.28 rads or radiuses, just like it would be here with a real circle. So remember, you got 6.626 times 10 to the negative 34th joules, right? But it's a joule second per cycle. What's the second for? It's for getting, because you want to use this E equals HF, right? Frequency times your Planck's length, or your Planck's constant, right? So each one of these things are packets, a second packet of photon, right? And this H here says that every second, right? You take that second, that joule second, right? And you count out all the cycles, all the sine waves. Like here's this 1 sine wave, here's this 2 sine waves. This packet has 3 sine waves. And then he's saying, hey, give all the sine waves, give them all 6.626 times 10 to the negative 34th joules. That's what, this one has 3 times H. This is 1H, 2H, 3H. Why? Because each full sine wave is an H of joules. And this one has 3 humps, but you only count up the ones in 1 second packets, okay? And I'm going to do a video about Planck's constant and the reduced Planck's constantness, and about angular momentum, which I bring this up about rads. Because if you use your units, your proper units, right? Not on a test, but just when you're doing math by yourself. If you use these proper units the way I'm using them, everything makes sense. Everything falls into place, just like down here with the joule second. Everything makes sense as soon as you put in the rest of your units. And they tell you not to use these units like these cycle and rad units. They are units. Stop not doing them. Unless you're doing a test or something, because nothing makes sense without them. Okay, when I get down here and I was telling you about a joule second, none of this would make sense if I didn't put on the per cycle. If I didn't add in the